Honestly, it's the hallway track. Like, the spaces where I've learned the most at CppCon have been in the evenings, hanging out with people over a drink or at dinner and just chatting.
All right, welcome everybody. First thing you might notice, there's a bit of a bug in the talk. This was supposed to be Greg Law and Mike Shah. Mike has jilted me at the altar. But you know what? Screw that guy. We're going to have fun anyway. We don't need him. No, I think Mike's gutted that he couldn't be here today. But so you just got me. But yeah, we'll work through this. So there's quite a lot of content to cover. I'm going to go fairly quickly. This is a back to basics talk. So if I make a mistake I often make is I assume things might be known when they're not and not clear. So please, anybody, just shout out, put your hand out, shout out anytime I say anything that you're like, what? Right? Because if you're thinking that, at least some other people are probably thinking it as well. And maybe we get a bit more of a discussion going, right? It's always better, I think, when these things are interactive rather than just me sort of standing up here, monotone, talking through it. Right, okay, so let's get going. So here's the thing, right? Programming's hard. It's not really a human thing to do. The level of precision that you need is just, well, it's quite inhumane maybe sometimes, right? I mean, how many lines of code do you think you can write and have it work first time, like proper code in a normal way? I like to think of myself as an okay programmer. I reckon for me it's like 10, maybe. Right? How many lines of code can I change in an existing project and have it work first time? I reckon that averages to less than 1. Okay? So it never works first time. Software is really hard. And if it isn't tested, it doesn't work. Right? It's a kind of rule of thumb. And if by some miracle it does work today, it will stop working at some point. Something will change around and your code will stop working. So everything has to be tested. Otherwise, it's just going to be a lot more pain down the road. So here's the kind of classic old waterfall picture, right? We write the code, we add some tests. And so writing the code is this like, yeah, you know, God mode kind of universe brain. It's the fun bit. We're already, and then we have to do some testing and some debugging. And that's kind of like the washing up. And then we can, well, obviously it doesn't work like that, right? Software engineering has never really worked like this. There's this sort of rumor that in like the 80s and 90s, it used to be like this, and then we invented Agile, and it's no longer like this waterfall process. It's not true. It's good software engineering has never been done like that. It's clearly just a big anti-pattern. It does still happen, and it did happen then. It's not how it works, right? What we want really is something that looks maybe a little bit more like this. If we're going to be waterfall-y, we're going to start with the tests. Right? You start writing the tests before you've written the code that the tests are testing is a really good test-driven development, it's called, and it's a really good way of doing things. I'm a big believer in it. Then we deploy in whatever way we deploy when the tests are fully debugged and the code is done. And then there's probably still lots of bugs, right? And we're going to find new issues. And so when a bug gets reported, maybe by deploy, what we mean is we're going to push this to CI and some of the CI jobs are going to fail, or maybe we actually deploy it for real and someone gets upset because something's not working. And the first thing we're going to do on receipt of a bug report is write a test to reproduce the bug, right? And that test goes into our regression test suite. And again, if it's not tested, if it does work today, it will soon stop working. So we keep doing this, and it builds up our battery of tests. I think, in general, you know, so quite different from this thing with testing kind of at the end. Actually, programming is more about testing, writing test code. I mean, hopefully very, very few of the tests, the minimum of tests are manual. Again, still happens a lot. I spoke to someone working in IT and healthcare, and they were talking about their test scripts. And I said, okay, that's cool. So what, you know, I'm just interested, what scripting, you know, what frameworks are you using? How are you doing your test scripts? You know, and she said, oh no, they're Word documents. The test scripts are Word documents, and we follow through the Word document and we check that everything works each time. It's in healthcare, it's terrifying, right? So hopefully the tests are code, right? And that is the programming. I just thought quickly before this talk, I thought, I wonder what it's like. So where I work at Undo, Let's have a look at our code. So I thought I'd just have a quick, this isn't the whole repository, but this is kind of the core of the engine. So if we go like that, I think it should tell us roughly how many of lines. No, that's not right. What does that? Oh, sorry. There we go. So about 420,000 lines of code and over 1 million lines of tests, right? And I think that's kind of normal. That's kind of, I think that's what you should be looking for. There should be twice as much test code as code that's being tested, because programming is hard, writing tests is hard, but it's like, it is part of programming. So I just thought I'd put this meme in here because I quite like it. There is a whole thing of test in production. This is a C++ conference, so I think hardly any, that doesn't really apply here, right? I think most C++ code is not going to be tested in production, right? Some of it's like going in airliners and stuff. Whatever it's doing, you're probably not testing in production. So yeah, software development is basically about testing and debugging. It completely dominates, especially debugging actually, but the test and debugging even more perhaps than the test code. Or at least software development done right is basically test and debug. Actually, I think I can, no, not done right. It's always going to be about testing and debugging, and it's up to you how much time you want to spend debugging and fighting it, right? And if you do the investment up front in the testing and you learn the tools and how to debug, you can spend a lot less time doing that stuff, but it's still going to dominate. It's just like, is it 90% or 60% of what you do? So I think some rules of thumb. So good tests, they should be independent, right? So the test should live on its own. It should be testing, ideally, especially for unit tests, which we'll get into in a minute, should be testing one thing, right? It should be very clear about what it's testing. And they should be repeatable. You really don't want, I mean, this is the ideal, they should be repeatable. So we don't want to have these flaky tests that fail one run in 1,000 or something, right? Those are just a nightmare. It's unavoidable. Everybody has flaky tests. I did a talk a while ago where somebody claimed, they claimed that all their problems in production and all their tests were fine and didn't have any flaky tests. And it sort of, someone else commented that, well, if you've got problems in production and all your tests are passing, then your tests aren't very good, right? So we always do have flaky tests. They are kind of a part of life, but we have to really kind of strive to eliminate flaky tests as best we can. And you have to have a kind of zero tolerance approach to it. The trouble with flaky tests is that flakiness begets flakiness, right? The developers, once you get, every project, hopefully, has a decent-sized test suite. And if that test suite can run on an unmodified main checkout of the repository and not pass cleanly most of the time, then what happens is developers stop trusting the tests. And you get into this pattern where I make some changes, I run the tests fail, but I don't think that's my fault. It's got nothing to do with the code that I wrote. I'm going to try again. I'm going to rerun the tests. Yay, I got lucky, and then I merged the code. And so sometimes you just were unlucky and you got a spurious failure, but you've no way now to prevent more and more flakiness creeping in over time. And so the test suite will just become less and less reliable, and it just becomes quite an unpleasant, like your job becomes unpleasant if you have a flaky, unreliable test suite. And it's one of those things that the longer you leave it before you tackle the problem, the harder and the more expensive it gets. If it's too expensive to fix it now, it's going to be even more expensive to fix it in a year's time. But the problem is going to be even more expensive in a year's time. So you have to kind of get on top of it, and you have to have this zero tolerance for a flaky test. If the test flakes out, you've got to, at least my rule of thumb is, at least progress the investigation of that. Even if all I can do is add some line of logging or some assertion somewhere, I'm going to move it forward so that the next time it flakes out, we'll have a bit more of a clue about what's going on, right? Hopefully I can do better than that, but that's kind of the minimum you can do. And the other thing is that tests should be fast. Again, the longer tests take to run, it just slows down the development cycle. What you really want is this tight feedback loop. So I think a lot of time people don't put enough emphasis on tests being fast. You want, most projects have their big, ginormous test suite that might take 12 hours, it might take longer. But that's not what you're running as a kind of matter of course. So I'll get into that in a bit more in just a minute. But we have these tests at different level, right? So unit tests, which I'll get into in a bit more, and when we're just testing individual bits of functionality. Integration tests, when we're testing that things work together. System tests, where we're testing kind of the whole system. I'm not going to talk about acceptance tests. That's really important, but that's kind of more, do the users actually enjoy the software that you've produced for them? It's kind of out of scope. But yeah, we do these different kinds of tests at different points. So a lot of it is interactive and iterative, right? If we're doing test-driven development, we're writing the test and we're running that, perhaps again and again as we kind of sort of asymptotally approach on correctness. And we really want those to be quick. We want them to give us quick feedback. It's very disruptive to development processes if tests take upwards of a few minutes, because no one's going to wait for a few minutes. You context switch onto some other piece of work. And so there is no such thing as a few minutes. It ends up taking a few hours. Then you've got this so those should be nice and quick. You want them to be within a few minutes at the maximum. Then you've got pre-merge. So got my branch, I've changed my code, I think it's ready to go. And I've got these barrier tests, if you like, that I'm just going to make sure everything is good to merge this into the main repository. Now they can be a lot longer. The shorter the better. At undo, we try and keep them less than 30 minutes. Sometimes it goes up and down as, people tend to add tests to these test suites, right? You add a regression test, so the test suites just grow. So you have to then do that gardening to kind of keep on top of it and keep them quick, but they're going to take a bit longer, obviously pre-merge. And then post-merge, right? So continuous integration testing. So I'm pretty confident my code is good. I merge it into the main branch, but I'm going to throw the full kind of battery of really aggressive tests that might take 12 hours, might take a week to run, and they might tease out this safety net, catching the things that somehow, despite all our efforts, did make it into the main branch, right? So that's kind of just some sort of setting the scene, I guess. For unit tests in particular, but it applies equally to system tests, this is a nice way, I think, of thinking about documenting the tests, right? You want to say, given something, when something, then this is what I expect, right? So here's a little example. Given a server with a maximum number of accepted connections, when a new connection attempt is made, then the error code e2many should be returned. I don't think e2many is a valid error code, but you get the point, right? And that helps us document the test clearly. This is something that we had a bit of a bad history of at Undo, was we were always quite good at writing tests, as in the process of producing the tests. We didn't used to be very good at documenting them. And so, years go on, 3, 4, 5 years goes on, the person who wrote the tests may even have left the company, or it might have been me, and I can't remember back past last week. And the test is, maybe it's flaky, maybe something else. And someone said, well, do we still need this test? Can we get rid of it? Is it important? I don't know. I didn't really do a very good job of documenting it, so don't know. Now it's scary to remove it, so they sort of stay in, and the test suite just grow and grow and grow. So good documentation is important for the future you or your future colleagues in 1 or 2 years' time, when you have to do this constant kind of gardening of the test suite. But this kind of structured way of thinking also helps us keep the tests to be independent and testing one thing with clarity about what they're testing. All right, any questions on what I've said so far? Anyone disagree with everything that I've said so far? It's a little bit kind of, well, not controversial, but some of it's opinion rather than hard fact. Okay, maybe it wasn't controversial enough. Let's try harder. Yeah, all right, so I'm going to talk a little bit about unit tests. So we're going to test this module in isolation, right? Very, very useful for making fast, repeatable tests. The bugs that they turn up generally are pretty easy to fix, because we're testing a fairly small part of code. And so if something goes wrong, it's usually pretty well defined. I'll talk a little bit later on about what makes bugs hard. And we get this really nice tight feedback loop, right? It's all about feedback loops. Tighter a feedback loop, the more productive and happier everybody's going to be. Problem with unit tests is assumptions, which I'll come to, but yeah. Assumptions, I only learned this the other day, but assume makes an ass out of you and me, which I thought was quite cute. But yeah, totally it does. And that's the big that's the gap in unit tests. But that's not to discourage them. They're still very useful. You just have to know what they're good at and what they're not good at. There are lots of unit testing frameworks out there. The most popular by some margin actually is Google Test. This is from Stack Overflow survey, I think, or maybe it was JetBrains. I think it might have been a JetBrains survey. You can see here, so 26% said they don't write unit tests. So that means basically 3/4 of people do. And it might depend. Unit test, there is, what exactly do you mean by unit test? Whether this test counts as a unit test. Some people get quite almost religious about it, and they get very pedantic about whether the thing is or isn't a unit test. So I suspect some of those 26% are people who kind of feel not worthy of the name unit tests, but I expect a bunch of them are doing it. But anyway, Google Test is the clear winner with Catch 2, Catch and Catch 2 in second place, and then we get into this kind of longer tail. Google Test or G-Test, by the way, this survey matches my own experience of talking to our customers. We do see Google Test more than anything else, definitely. And here's a really, really simple advantage. I mean, I just copy pasted this off the Google Test GitHub page. So, well, you can go and read it yourself. But you can see how, it's very well defined, narrow. We're just testing narrow things and making sure that the factorial does really return the factorial. I haven't actually checked the maths on it. I assume it's correct. And Catch 2, kind of the same, right? Same but different. It's got certain advantages. From which one you prefer is kind of up to you, or there might be others. But they all kind of look the same. But one of the things we need to do with unit tests is mocking or dependency injection, right? And so if I've got this module, here's my module, beautifully presented, but it's just a module. It's a small, it's a class, or it's a I don't mean necessarily a C++ module. It's just like a piece of code with a well-defined boundary, and it lives in a system, and it talks to all these other bits of code and network and users and everything else, and has all these inputs and outputs. And so when we mock the interfaces, we're kind of giving these mock versions of the interface, so we can give well-defined stimuli to our bit of code and assert that it really does exactly what we expect it's going to do, makes them very repeatable, good for fault injection. So you can do things like this through mocking. So, I've just got read and write, and I can provide versions of those, which, again, this is Google Test, I think, and sort of express in this declarative way what we expect. And I can put errors in here, right? I can see that times 4, so it's going to repeat 4 times. Once it's going to return 100. The other time it's going to return -1. I'm going to mock an error from the read system call, right? Make sure that I get that error handling right. More than 50% of bugs that escape the first level testing are due to error handling. And when I say that, I just completely made that up. I have no solid data for that other than my personal experience, but I will stand by it. And if anyone has got data on it, I will happily bet them a beer later on that it's the case, because error handling tends not to get tested. I'll come to that in a bit. There's a bunch of these memes around, right? Unit tests passing, but no integration tests. But the problem with unit tests, well, not the problem with unit tests, it's just the kind of boundary of what they're for is they test that bit of code in isolation, but they don't test the whole system as a whole. And you can have these bits of code, these 2 kitchen drawers here that both work perfectly, but together they don't work. And that's very common. So we need the system level testing as well. We need to test all the modules when they're glued together, work in the right way. One of the big things with unit tests as well, though, is assumptions. So the reason, maybe here you could say there's an assumption of whoever put that drawer in that they sort of assumed that they wouldn't need to open both at the same time, or even either fully, I guess. They assumed that handles weren't there, right? They forgot about the handles. And that's kind of a nice metaphor in a way, and we often forget about those error paths, and I see a lot of people kind of put error handling in that doesn't have any testing because it's too hard to test. And it's like, if it's not tested, it doesn't work. There's going to start to stray into now how we produce the code, right? So I just think you just can't have too many assertions. and contracts and everything else. Yeah, but so coming back, sorry, my slides are a bit out of order, to test or panic. So I used to think 5-10 years ago that, well, I'm going to try and handle, I used to think that assertions shouldn't be fatal, because my other completely made up statistic is that 50% of assertion failures are because the assertion turned out to be bad. There's nothing wrong with the code, it's just it was like an overzealous assert. So why make them fatal in production, right? Why upset your users and customers when half the time it's just because you put a bad assertion in? I changed my mind on this a few years ago, partly because that philosophy kind of was all fine until we started getting real customers. And it turns out when your assertions just print a warning, say this is wrong, please report this, we found out 99% of our customers would not do that. They wouldn't report it. If we crashed hard, then they totally would report it because it was getting in their way. So in the end, we kind of said, no, if the assertion fails, we're just going to panic. Panic as in just abort is perhaps the right word to use actually rather than panic. And so if you don't have a test case for that error handling code where read from the file system fails, don't have any error handling code, right? Just abort. If you need to handle it, if an abort's not acceptable, then you need to have test code for it. Because if it ain't tested, it don't work. So I'm trying to be a little bit more controversial now. Surely not everybody agrees with that. I'm going to end up like getting too close to the code of conduct or something if I need to get. Yeah, okay. So it's actually a little bit of history. So many of you will know Unix, of which Linux is a variant, exists. It's a pun on the word multics, which was this 60s era big operating system that was supposed to kind of solve all of the problems and was going to be the operating system for the future. Completely failed as a project. Unix won. Many things were better about Unix than multics, but one of them was the panic. All right, they would panic on various error paths rather than multics had this kind of philosophy of every error is going to be handled gracefully. But you just end up with like huge amounts of complex error handling code that isn't tested and doesn't work. So do what Unix did. Yeah. And the other thing I would say in tests in particular, do not sleep. Now, I don't mean literally don't sleep, keep on writing tests 24 hours a day, obviously. Going to make up another percentage now. 49% of flaky test failures are because somebody somewhere is synchronizing via sleep, right? They're like, do a thing, kick off, I don't know, send off some request to some server. That thing's gonna write a file, and then I'm gonna read that file and do something with the contents, say. And I'm gonna sleep for a second or 10 seconds or a minute, whatever, to let that thing, there's definitely time the file would have been produced, now I can read it. And that will fail. You cannot wait long enough. Something, especially these days, a lot of testing is done on AWS or whatever cloud provider, and they're probably not bare metal machines. You might get migrated from one machine to another. Like things can go, your processing, the clocks get out of sync, and so the operating system starts running clocks faster in order to catch up with time. If you've got to sleep anywhere in your tests, that's almost certainly flakiness waiting to happen. Show of hands, who has sleeps in their tests some of the time? Oh, such an honest bunch. I love it. And do you agree with me?
Yes.
Yeah. Yeah. So everyone who has sleeps wishes they didn't. They're very hard to avoid, right? You have to think a lot harder, and you sometimes have to write quite a lot of test code to avoid the sleep. But yeah, it will hurt you. Another thing to think about is like how testable we make the code. I was actually speaking to somebody earlier today. I added this slide about half an hour ago. So I was speaking to somebody earlier today who talked about one of the problems they have is this almost infinite space of configuration that their tool, just different configuration options. And some of them are Booleans and some of them are integers. And he said, he worked it out, it's pretty clear that if you summed all the different possible permutations of all the config options for this tool, that's more particles than exist in the universe, right? The visible universe. So how do you test that? How do you possibly test that? Clearly you cannot. So yeah, the more you add these config options, okay, great. But if I add one Boolean config option, I've, in theory, just doubled my test coverage that I need, right? So be really careful about, yeah, that's nice to have that config option, but maybe you should just be a bit brave and choose a value. And then also, yeah, how deterministic is the code? Again, I mean, sometimes we need to have those config options, and often, almost always actually, code cannot be completely deterministic. If it's something like a compiler, hopefully it is. Right? If you read the same source file and the same compile options, hopefully the same binary comes out at the end. But that's the minority. Usually there's some human input or some other thing that means it's unique. When I make a spreadsheet, hopefully no one else has made the exact same spreadsheet ever before, right? But still, you want it to be as deterministic as you can. So I have 33 minutes left, and I think I'm about halfway through the talk, which is excellent. This is where it all goes off the rails. Right, yeah. So testing is cool and all, but it doesn't matter how much testing you do. Most programmers spend most of their time debugging, as I said. Never works first time. Well, here's somebody who puts it much better than I could. You may know this quote from Kernighan, one of the inventors of Unix. It says, everyone knows that debugging is twice as hard as writing a program in the first place. So if you're as clever as you can be when you write it, how will you ever debug it? Now, that's very pithy and right. And what he means here, this comes back to the previous point, right, is, yeah, basically you're not as smart as you think you are, and the computer will outsmart you, will make a fool of you. So give yourself that margin for error when writing the code. I had another kind of analogy for this was, I'm not a motorcyclist, but somebody was a motorcyclist, so that you often see these young, usually men, riding their motorcycles around at 100 miles an hour, and you look at the older motorcyclists. It's not just Darwinian that like the ones who ride at 100 miles an hour got selected out of the gene pool, but it's also that they've learned, hopefully the easy way, but they've learned that they need to leave a lot of margin for error. Yeah, they could go around that. They could probably go around that corner faster than the 20-year-old, right? Or as fast, but they're not going to because like shit happens. So I like to keep that in mind when writing code. Just keep it simple as you can. But there's another, I think, corollary to this statement that if debugging is twice as hard as writing the program in the first place, then debuggability is the limiting factor on how good our code can be, or how good at debugging we are is the kind of rate limiting factor on how good a programmer we can be. Like whatever your definition of good, whatever your metrics for good is for your program, how quickly it runs, how small it is, how quickly you can write it, how extensible it is, if you can debug it twice as effectively, you can make it twice as good. You can be twice as good. And I really feel that this is such an underappreciated thing. We don't really teach it in universities. We don't really talk about it. So thank you, everybody in this room, for coming to talk on testing and debugging. I wish there were more such talks over the week, because it's so critical. You might remember this, quite popular a few years ago, XKCD. Yeah, they're goofing off because their code's compiling. Why is the code compiling? This is you don't know why the code's compiling, right? But if I told you 88.7% of the time the code is compiling because they added a print statement, right? I'd love to know for real what percentage of compilation, not like CI builds kicking off and stuff, but like manually triggered compilation because someone added a printf or equivalent. Yeah, well, I just told you, 87.9% was it, whatever. Right. So debugging is, so I have a set of expectations This is what I thought the code that I'd written or someone else had written was going to do. And reality has diverged from my expectations somewhere, right? And the purpose, the job of debugging is to figure out where did reality diverge from my expectations. Usually looks a bit more like that. But, and this can be really hard, right? So sometimes we're lucky. Sometimes the program fails in such a way, maybe an assertion fails, which is why assertions are really good. Assertion fails and we just know, oh, yeah, oops, I don't know. Yeah, of course, read could return short. I'd forgotten about that. I'd better fix that. But usually that's not the case, right? In fact, we spend most of our time, at least, on these bugs where that's not the case. And we have to just keep on going. We keep adding more printfs or doing more things to get these pieces to the jigsaw puzzle, that piece by piece we're collecting, right? Or maybe it's a kind of more like a Sherlock Holmes. We're getting clues. And eventually we get the final clue where the whole puzzle kind of falls into place. But I think what makes bugs hard is what I alluded to before, and one axis is the time that elapses between the bug, right? So in that little, go back here, this thing, right? How long it is between those arrows diverging is a key determining factor in how hard the bug is going to be. Well, I said to fix, I mean to root cause, right? I mean, if you actually, once you've diagnosed the bug, it is usually, not always, but 94.6% of the time, it is pretty easy to fix. It's diagnosis that's the hard bit. And one of the two big things that makes bugs hard to diagnose is how long happens between the bug itself, that bad line of code executing, and basically you noticing. And this is why assertions are so useful, right? Because they narrow that window. The other thing that makes bugs hard is how deterministic are they? Does it fail in the same way every time? Or does it only fail one time in 1,000? Or maybe it fails every time, but every time it fails in a different way. So I'm like getting these pieces for that jigsaw puzzle that I spoke about, but it's a different, every piece is for a different puzzle, a different jigsaw, like it's impossible, right? And particularly when we get up here in the top right, where things are both a long time between the actual bug and you noticing, and in a kind of non-deterministic way. Those are like super hard, like sometimes bordering on impossible to fix. And then, oh no, that image hasn't worked. This is a bad sign. Anyway, that was a little Breaking Bad Heisenberg thing. It was quite cool. You get the Heisenbergs, right? So when we add a print statement or whatever we're doing to try and get more clues out, makes the bug go away or change in some way. There are loads of different kind of bugs. Logic bugs, I mean, maybe every bug is a logic bug, but I mean, you know, it's like an on-off by one error or something. Pointer errors, you know, famously in C and C++. Error handling, I already talked about. Race conditions is a good one. You know, where I've got multiple threads. Actually, again, in my experience, the canonical race condition, all the, you know, 201 or all the textbooks, all the web tutorials on a race condition is two threads, both accessing a single piece of data, probably doing a non-atomic increment of it. And like, yes, those data races do happen, but I think much more common is a race between, is a non-data race, a race between your program and kind of the outside world. So I'll give you an example of one happened a little while ago at Undo. In our testing code, there was just this really innocuous bit of Python that said, at the end of the test, if the directory exists, remove the directory. And that ran like fine for, I don't know, millions of times until one time, another copy of that test was running in parallel. And so it did the check of the directory existing, and the other one did the check of the directory existing. Both said yes. This one removed the directory, and then this one crashed because it tried to remove a directory that didn't exist. Really common, right? Or, you know, signaling, or like I mentioned before, that file not being updated in time. So there's loads of different race conditions, and the canonical data race is usually not it. I think also people are too quick often to diagnose something as a race condition. So if they see like a flaky failure of some way, right, fails 1 run in 100, must be a race condition, right? Because that's what race conditions do. Well, it might be, but it may not be. It could be due to memory allocation. It could be due to user input. It could be all kinds of things. We had another one we had, took us quite a while to figure this one out. In our overnight CI testing, this is going back a few years, so we had limited testing hardware available. So we'd run a whole bunch of tests overnight, every night. Now we just run all the time. But, and we had this particular test that would fail every night. And every day, when we tried to diagnose what was going on, we couldn't make it fail. We tried running it under load. We tried all kinds of things to try and make the thing fail in a way that we could get that feedback loop, that type feedback cycle and work on it. Couldn't do it. Eventually, we figured it out that it was scanning the time of day. And if the time of day started with a 0, it would fail. So when it ran overnight, it would fail. When you tried it in daytime, it also told me that none of our programmers work before 10 a.m. But that's an example. It's not a race condition, right? It's just something's causing the failure to happen in a non-deterministic way. I think interface assumptions are a biggie, especially, that's the thing with unit testing, right? We just assume that the interface can't do that, right? And didn't realize that I wasn't allowed to pass in this value, or more likely, didn't realize that it would, return that result, or I could call it this and then that, but I could call foo then bar, but I'm not allowed to call bar then foo. Like, just a whole bunch of implicit interface assumptions that trip us up. I'm going to do a bit of live. Oh my God, that's no, that has not helped. Lives. What other kind of bugs? Live slide editing. I haven't got enough pixels here. Maybe that'll work better. Go on, shout out some other types of bug. I know it's after lunch. Yes.
In video game, we do have some bugs when using shader that are not compatible in other platforms.
Oh, right, yeah, so platform incompatibilities, yeah. Yes?
It's kind of related, but backwards compatibility in general.
Yeah. Ooh. Backwards. Why do you have compatibility is such a hard word to type under pressure? I think I don't know whether I got it right. It's so small, you can't check. What else? Go on, give me 2 or 3 others, and then we can move on.
It could be algorithmic errors.
Algorithmic errors. Yeah. Are you just deliberately choosing hard words to type? One more.
Input output errors, like file IO.
Oh, yeah. That's easy to type. IO errors. Yeah, right. Yeah, and general kind of, yeah. I might put that under error handling, but, okay. There we go. That was stressful, mainly due to the lack of pixels. Right, so when we're debugging, the impossible happened, right? If I thought that was possible, I wouldn't have the bug in the first place. And another little quip on assumptions. This is probably the 3rd or 4th time I've used this word because it's so key. An assumption is something you don't realize you've made. Okay, what does this represent? Rubber ducking, yes. Yeah, so which is where you explain, it came from, I believe, in a student class, people learned to program, and the professor, you must have all done this 100 times, right? You say to somebody, I've got this really impossible bug. Can you help me with it? And you explain the symptoms you're seeing, and during the process of explaining it, you go, oh, I know what it is now, right? And the professor got bored of listening to this all the time, so he put a rubber duck in the classroom for people to explain it to. But you could do another version of this I find useful. If you don't have anybody to hand and you don't have a rubber duck, then you just write it down. I find writing down what I'm seeing with pen and paper, but I find it works better with pen and paper than typing because I can type a lot faster than I can write. So as I write down what I'm seeing, I'm having to think quite slowly about what I'm saying, and the assumption that I didn't realize I'd made often comes out. So I find I write down, it's what I'm seeing is completely impossible, there's no way, because I've checked this can't be that, and it never, oh. Sometimes it goes a bit like that, but hopefully it's a bit more like that. Yeah, right. When you smell smoke, act. Now, this doesn't work brilliantly because this morning there was the fire alarm and we all then were told to come back in again, and then it went off and then no one else went back outside. So maybe, but generally, whether or not that fire alarm was going off, if you smelt smoke, you'd probably go and have a look at what's going on. I mean, maybe you ran away, depending on how brave or cowardly you are, but you're not going to ignore it and just carry on, right? And the same is true when you're debugging something, or in general with software. When something doesn't seem right, like, I don't know, maybe I'm stepping through some code in a debugger and I'm looking for this bug, and something else returns, oh, I didn't know that could return negative value, or I didn't know that value could be null. It doesn't seem right. Pretty sure it's unrelated to what I'm working on. I'm really busy. I've got to fix this bug by the deadline, and so I'm just going to hear no evil, see no evil, kind of move on, get on with what I'm up to. It is never a good idea to do that. Again, 54% of the time, that unrelated thing that looked weird, that you decided to just ignore, turns out to be directly related to the bug you're chasing down. You just hadn't realized it because the assumption was something you hadn't realized you made. And you're kind of in that area, right? If you see it, it's close to where you're looking. So even in a completely short-termist, selfish kind of way, you should hunt down that weirdness and fully try and understand it. But certainly, your future self will thank you, and your future colleagues will thank you for doing that, because you're halfway there. If you see this weirdness, if you see that thing being null that you think probably oughtn't to be null, you're not more than halfway there. You're 90% of the way there, right? Whereas if you just get a bug report from production, because that thing was null, it's just massively more difficult to track that down. So when something doesn't seem right, something seems against what you expected, hunt it down and allow yourself to do this kind of depth-first search for what's wrong. And it might feel like you're wasting time and you've got deadlines to hit, but overall you will be much more productive if you do that. And then on to the last bit of the talk, which is about the tools that are available for debugging, and there are many. And I'm going to just give some this is not a tutorial. We're not going to go into, you're not going to come away knowing any of these if you don't know them already, but you at least will know they exist and maybe what they're for. And hopefully when you next need them, you'll go and look them up and try them and get used to them. Okay. Let's have, really, really quickly, because I'm just curious, I want a show of hands for everybody who's used GDB in the last month. Oh, about half. LLDB? Pretty small number. Valgrind? 1, 2, 3, 4. Okay, actually somewhere under LLDB. Sanitizers? 1, 2, 3. Ooh, a little bit more than Valgrind, but not many. Okay. strace or ltrace? Ooh, getting niche now. The standard library debug modes. No, very niche. Time travel. 1, yes? Is that it? 1? I don't mean actual time travel, I'm talking about time traveling debugging. But just 1? Right. I'll convert you all by the end. Okay, so GDB is much maligned. There's a lot of rumors that don't, just from how it used to be, it's much, much better these days. It's pretty solid. It's good at debugging threads. There's a lot of misinformation out there about it. There's a lot of it, right? So I'm going to quickly show, because I always show this one because it is, I think, the single most useful thing of GDB, and that is not known. So here's like my really simple program. -G3, by the way, just gives me more debugging information. Plus. So if I run that in GDB, start, so here's my code, but if I go 2e enable, much better, right? And now as I go through the code, we can actually see what it's doing. By the way, like in all modern systems, this is using a bit of SDL, and that will be pretty printed like that. So that's GDB. There is loads and loads of it. I have like hours of talks I can do on GDB, but not this year. LLDB is basically the same, but different. Oh, it doesn't have start. I have to go break main and then run. But it's basically the same. And I think, oh no, it's totally different because rather than TUI enable, you have to write GUI, I think. Yeah, there you go. And then that's basically similar. Let's get out of there. You can use whichever you prefer. There's a rumor that I've heard a few times that, well, I think a lot of people believe, and this may be true, that LLDB works better with code generated by Clang, and GDB works better with code generated by GCC. Probably true. There's a rumor that Clang generates better debug info that I've heard a few times than GCC. Not true, and empirically not true. But yeah, basically they're the same. Right, Valgrind is super cool. Let me show you Valgrind very quickly. So here's a program that has a bug in it, right? Because it mallocs 10 bytes and then accesses the 11th byte. No prizes for spotting that one. But obviously, this kind of error creeps in all over the place, all too easy. Yeah, should have been using Rust, but you know, like we don't. That's a bit glib because there's like a trillion lines of C and C++ out there. So if I run that, actually it looks like it works. It doesn't print any output, but it doesn't crash because I got away with it. But if I run it through Valgrind, it tells me, yeah, look, it tells me that at this line of code, I was off the end of this size 10 alloced memory happened at buffer.c line 7. Like how useful is that, right? I mean, if it was a million lines of code and I was trying to look for that buffer overrun, that would be like impossibly hard. There's actually, Valgrind is actually a suite of tools. There are things that look for race conditions and cache issues and all kinds of things. The memcheck is kind of the default tool. You see, it's super easy to use, right? Actually, first time I heard of Valgrind, like an embarrassing, like probably 5 years, courage to use it because it sounded so magical that I thought it's got to be pain. And I'm going to have to rebuild my program, and there's going to be dependencies, and I'm just going to add a printf, right, and do sword fighting. And eventually, I was in a situation where I think I didn't have access to the source code, and I was just stuck. And I thought, well, there's nothing for it. Here goes. This is going to be that other XKCD where they try and install BSD and end up being circled by sharks kind of came to mind, and this is going to be an awful experience. But here we go, and it was like sudo apt install Valgrind, ran Valgrind, there it was, told me exactly what was going on, and I was like, okay, that was mixed emotions, because like really good, but also really embarrassed that I'd spent so long plucking up the courage to use this thing that just works a lot of the time. Nowadays, there's sanitizers, which are both better and worse. So it's a kind of similar thing. Actually, got tools. It's a set of tools that does mostly the same thing, but it's not an external, tool, but it's a compiler option, and it changes the way changes the code that's compiled. And now I run it natively, and slightly more colorful, but basically the same thing. Pros and cons, it's much faster. Like Valgrind is slow. Sanitizers are like 2x to 5x, they claim. So much, much faster. Does use a lot of memory, but you have to change the code. You have to recompile, right? Which is sometimes fine, sometimes very inconvenient, sometimes just not possible. Also, I believe that the famous XZ attack from like a year ago that was like super sophisticated, that got caught by Valgrind. That got caught by Red Hat people running Valgrind on some innocuous thing and smelling smoke and following the line of inquiry, and that turned out to be the whole XZ thing. Sanitizers, that's actually loads of sanitizers. Look at all these sanitizers. There's another sanitizer called Undefined, which covers most of the ones that you want, because some of these are just sets of other sanitizers. Some of them are mutually compatible, but you can just use the Undefined sanitizer, and it gives you basically everything you need. Very useful. You can set these environment variables in for GCC or for Clang. For the libc, which will just do sanity checking, like making sure the vectors are accessed out of bounds and whatever. You can also have these debug versions in GNU. You can have these debug versions of all of the containers, so you can select. You don't have to turn it all on or all off for the checking. Why the default for things like vector doesn't range check, and you turn it off only if you really need the performance, I don't understand. I think that's daft, but that's where we are. strace and ltrace is very cool. So strace is really good for getting a sense of what the program is doing. So if I go strace, I don't know, ls, these are all the system calls that typing ls did, right? And so often you can find system calls that are failing and some bad error handling, and you can start to diagnose things, particularly if you're debugging not some code you wrote, but some program or some system. Nice thing with strace, by the way, you can do strace-p to attach the running process. You can do -k, and it will give you a backtrace for each of the system calls, which is kind of handy as well. These are just little tidbits, right? Okay, time travel. So just about time for my favorite demo. So in case you don't know, I run a company called Undo, and we make a time traveling debugger. And but the others are available, including RR, which is open source if you're on Linux, and there's the WinDBG on Windows has an inbuilt time travel these days, and it's completely awesome, and everybody should be using it. Actually, so this is, I usually use this image because time travel doesn't let you go back and change. Time travel debugging doesn't let you go back and change history. It just lets you go back and see exactly what happened line by line. So this is H.G. Wells' Time Traveler, where he doesn't really change history. All the other time travel science fictions, they tend to change things. But I'm going to show this one because for two reasons. One, that is a completely awesome Lego DeLorean, which you can win if you go to the Undo stand after this and come along to the little drinks party we're doing at 6 o'clock down the steps by reception, and somebody will win this completely awesome Lego DeLorean. Also does that. So like, why wouldn't you want it? I just think it might be a bit embarrassing if I won the raffle, but I'm sure I won't. But also because I've realized that this is quite a good analogy for time travel debuggers, because is this a car that travels through time, or is it a time machine in the shape of a car? Right, it's definitely the latter, okay? Just happens to be in a car. The form factor of the time machine is kind of cool, but that's not the interesting thing. And it's the same with the time traveling debugger, right? A time traveling debugger is not a debugger that can do a bit of time travel. It's an ability to do time travel that comes in the shape of a debugger. Let me show you a cool demo to finish on. Let's play, I can't remember what I was, I've got the right history. Let's play, I can't remember where it is, in here somewhere. Shortcut it. Right. Let's play Doom. Oh, the sound's not coming through. Sometimes when I do these demos, the sound comes through, but this one isn't. Actually, before I play Doom, I'm just going to that's the PID of Doom running there. So I'm going to get a time travel recording of that, like that. Yeah, so let's play Doom. So I always get a bit lost in this. There it is. Now, the point of I'm showing you this demo is because I don't understand anything about the Doom source code. It's pretty well written source code, I believe, but I don't know anything about it. But I'm going to show you how using time travel you can navigate through completely unfamiliar code. So here are some zombies. Let's shoot them before I die. That will ruin my demo if I die. Come on. Right, and that will do. So I'm going to quit that recording. So this is now saving out a recording, a little bit like a core file if you've used a core file, except unlike the core file gives you the program state at the end of the program, this gives you the state for effectively every single instruction that I'm running out of time. So that went here. I'm just going to, sorry, turn off that. So let's load that up into my time traveling debugger. Let's go to the end of time. And now I'm going to, I've got a command, show frame. The only thing, I said I know nothing about this program. It's not true, I know one thing. The video buffer is in a 2D array called video buffer. And it is 320 by 200. That's the only thing I know about the code. And so let's have a look at that. So this is the frame at the point that I stopped recording, not the point I ended the program. Actually, the program's still running. Yeah, program's still running. Quit. Yeah, return. Right, let's close the program down. Not at the time that the program ended, but at the time I stopped the recording. And here are some dead zombies. So I'm going to get some pixels here. So that is, I think, 115, down at the bottom, I can see that's 115, coordinates 115, 115, 123, 115, 123. So if I look at the 115 plus, that is the pixel in question. So I'm going to do last. So the last command is going to wind the tape back to the last time that pixel was updated, right? So I want to see when did that change. Seem to be drawing the screen, so that's kind of what I would expect. It's a backtrace. I'm going to reverse finish up a little bit. Let's see what we've got here. Still drawing the screen. It's got this. Okay, I'm drawing a sprite. That's interesting. So I've got this thing called sprite, spr. It's got X and Y coordinates. So I should have said, what I'm trying to do here is find out when in the code did I shoot that zombie? So this is the sprite. We're painting the sprite of that zombie. So let's go back to when it last moved, because that's going to be like when I shot it, it moved, right? So let's just go last on one of its coordinates. And this is project sprite. So I've got this. Oh, whoops, I didn't want to do that. You know, one of the nice things about time travel is when I go to a long place, I can just go back to where I was. So I've got this thing called thing. And it's got a member called health. I can see, yeah, that's probably not very healthy, I guess. That's less than 1. So let's go to when that last changed. And now let's show the video buffer at that point. And I'll zoom in a bit. There we are. That's just the point I shot that zombie. So I don't know if that was clear what was going on, but I was navigating through a real-world program and with no idea how it all hung together. But by following the data back in time, I could see exactly what happened and when. 10 seconds for your best questions. I think we can probably go over slightly if anyone's got any particular questions or comments or things I didn't say to talk about that you were hoping I would talk about. Okay, I'm going to ask a question of you. Who is going to go back and try time travel debugging of one form or another? Show of hands. More hands, please. Come on. Really? Like, you're mad if you don't. It's like, you don't have to use undo stuff. You can use other things. But as a concept, you're just, yeah, your future you will thank yourself. Right, we're at the end of time officially. I'm happy to hang around. I have some tickets here to our little drinks reception downstairs by reception, at which you can win the DeLorean. So if anybody wants one of the tickets, come and see me. Or if you just want to hang around and have a chat, also hang around and have it. Thank you very much.